We're going to start doing some more with special relativity, and in particular, we're going to talk about space-time diagrams. Okay, this is also known as Minkowski space, and I believe I am spelling his name correctly. But basically, it's the space for general relativity to take place in. It is different from our regular Euclidean space with x, y, and z. This has it has an x, y, z, and a time, and depending on the metric that is chosen, it's either positive in time and then 3 negative spatial dimensions, or negative in time and 3 positive spatial dimensions. Mathematically, they're equivalent. You'll get the same result. So whenever you're doing special relativity, you need to make sure you know what the metric is. And the same thing for general relativity. If you ever get to that one day, you have to make sure you know what the metric you're working in. Usually it's called plus, minus, 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 or minus, plus, plus, plus. But you need to make sure they have a different sign. If you're using like plus, minus, 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 where all the space-like dimensions are negative, then all of the space dimensions need to be negative, and the time-like ones need to be positive. So you got to pay attention to that. So we had worked on our the Lorentz equations, and I wanted to show you another way you could write these. You could actually write these in matrix form. We could have gamma V over C, and then we could have gamma V over C gamma. And so this matrix operating on the vector x, c, t should give us x prime c t prime. Okay, and so let's try this out. We'll just do a quick matrix multiplication. So this row times this column gives us gamma x here times here plus gamma v over c times ct. So this is plus gamma v over c times ct. That means the c's cancel, and it's gamma vt, and that has to equal x prime. And if we do just factoring out that gamma, you get x plus vt is x prime. Okay, and that's one of our Lorentz transformations. Obviously, this sign here just changes, from plus to minus depending upon what direction the velocity is in. If I had made this velocity negative, so put a negative sign here, then this would have been a minus sign here, and it'd be minus. But remember, either way doesn't work. Either way works. They're the inverses of each other. You just change the direction of velocity, and you change. This changes from the x coordinate to the x prime, make this a minus, and it changes from x prime to x. Then you can flip-flop it. And then let's look at the second one. It's this row times this column then. So it's gamma v over c times x, and then gamma times ct, so plus gamma ct, and that equals ct prime. And I'll tell you why we're going with CT in just a minute here, not just T. I probably should have mentioned that. If I divide everything by C, that cancels there, makes this a C squared, and just a little bit of rearranging, just flip-flop these, and factor out that gamma. You've got gamma T plus Vx over C squared. And that's the other version of the Lorentz. So we were able to come up with our Lorentz transformations from that matrix right there. And so this matrix actually is the operator that operates on your current coordinate system and transforms it into a new coordinate system according to what V and C are. And as we see, we get that right there. But if you've ever learned much about linear algebra, you know that if you have a matrix, the job of a matrix is to take a vector and transform it into a new coordinate system. And that new coordinate system is defined by what is called the column space of this vector operator, where that these two vectors here, this is a vector and this is a vector, are actually the new basis vectors for the space, and then this is that vector in that new space. So what I mean by that is, if we had, let me get a little different color here. If we had our space here like this, this was our regular space, and this is actually the Minkowski space. This is X, and this is CT. Okay? What this means is this operator moving into the X prime space, it actually is just a bending of both axes. So this would be the X prime axis. I'll do it in a little lighter color. The X prime axis would actually be moved up. Its new basis vector would be this vector. So it would be a gamma by gamma v over c up like this, and we'd have a new basis vector. And this is the X prime axis, what it would look like in the X space and the unprimed space. And then CT, this would be its new basis vector, which if you notice is just flip-flop from here, and it would look, like that. It would come off over this way, and it'd be CT prime. Okay? Now from that, the other thing that could have been done is if this had had negative signs in it, if it was going in the opposite direction, these also could have bent the other way, which would just be equivalent to doing something like saying, okay, these are kind of interchangeable views of it. If we look at it from the X prime CT prime perspective, right, where this is X prime and this is CT prime, then X would bend out this way, X, and CT would bend out this way, okay? So it can bend out the other way. That wasn't a very straight line, sorry. It can bend out the other way. Basically what I'm saying is I took this axis and I grabbed it and bent it down, and I grabbed this one and bent it over this way. And of course, as I did that, that pushed this one back out to the left, and it pushed this x-axis down below it. You could imagine just grab a hold of this, and bend them out, and push x and this CT, the unprimed coordinates with it, and it would bend them out the other way. Which just would, the only difference between these two is whether or not this v is negative or not. Okay, so you could see both of these, just depending on if you're changing perspectives. This would be from the unprimed perspective. This would be from the prime perspective. And remember, both of them have as much right to be claiming to be correct as any other. So why did I choose CT as this vertical axis instead of just time? Well, one, it works really well with this matrix, but two, it gives us this nice Minkowski space, and it does it in such a way that if you were to graph the path or the position versus CT, position versus time of the speed of light, it would go right in between them, because c times t is the distance light traveled in time t, right? Velocity times time. So this is actually a distance measurement then instead of just a time measurement, and that would mean that this axis and this axis would be identical for the speed of light, because this would be the distance light traveled and this would be the distance light traveled. So this would be the speed of light. It would go right along a 45-degree angle, and that's also true for the prime axes too. For any coordinate system, if we did like an x double prime, if we did another coordinate system transfer, we did an x, we had like a third person moving fast, or over here, this is always going to be at 45 degrees between these axes. It's always going to be directly between them. All right, so this is our speed of light. I guess I should probably finish right at speed of light. Okay, and we'll talk more about that when we come back to it in a little bit. But for right now, I want to talk about, well, how do we know how much to bend this over? I mean, are you gonna sit here and write this whole thing out each time and figure out what those numbers are and go through and do this? Well, not really. We can do it a little simpler than that. So let's take a look at what angle are these going to bend to. So what angle is this? And what angle is this? And the first thing you should note, and should be hopefully pretty obvious, is that these angles are going to be the same, because these vector bases here, right? This is the x-axis, the new x-axis angle, and the new y-axis. It just flip-flops. So, however far this one goes to the right and then up, it's flip-flopped that this one goes up, however much this one far went right, and this one goes right, however far this one went up. So it's going to be the same angle for both of these things. So we just need to figure out how do we solve for these angles. Well, if you remember, this is the basis vector for either one of these, so we can pick either one we want. So we might as well pick this one down low here. And if we pick that basis, right, this vector here, if I just draw in what that is, it would be this would be, say, the unit vector of it, that basis vector, and it would have an x component, horizontal component of gamma. So this component here would have a length of gamma, and then the vertical component would be gamma. I didn't leave myself for much room there, but this little part right in there would be gamma times v over c. And if I do the tangent of this, so this now makes me a nice right triangle. If I did the tangent of that angle theta, it would be equal to this opposite side, right, opposite the angle here. Remember, that's the angle in there too. It's got the same angle as what I drew way out here. It would be gamma v over c, that's the length of this side, divided by the length of this side, which would be gamma. Gammas would cancel, and then you would just take the arctangent of both sides, and you would get that this angle is equal to the arctangent, or inverse tangent, of v over c. Okay, and there you go. That's a result that you should be able to work out just by thinking about this. But if you're not, then this should be something that you should be able to use. This tells you how far does it bend over. If you notice, if you think about what happens here, this angle is going to get bigger and bigger as v gets bigger, but there's also a limit to where it would go. And if you think about this limit, what's the limiting angle that this can approach? I mean, think about the shape of the tangent graph, right? What's the limiting angle that this can approach but never reach? 45 degrees. So as v over c gets bigger and bigger, and in fact, if you did the arctangent of c over c, that'd be at 1. Well, where is the arctangent of where is the arctangent of 1? That's at 45 degrees. So this would bend up to 45 degrees at the speed of light, and this would bend over to 45 degrees at the speed of light, and then space and time would be right on top of each other, and that's one of those things that we can't really happen. Essentially, space and time would be on top of each other, and the way I would kind of think about it is they'd be, the two axes would be on top of each other, and any motion in space is a motion in time, and it's kind of like you're now everywhere all at once. So something going the speed of light, like a particle of light, is frozen in time. It sees all of its time positions at the exact same time, all of its spatial positions, they're all right on top of each other. And it's as though time is frozen for it. Okay? But basically that gets us what angle it goes to, and 45 degrees is the limit that we can approach but not get to. Gamma becomes undefined, in case you didn't remember that. So the next thing we need to discuss is, well, how does this affect the separation of the tick marks as this goes along? So if we look at this and we say, all right, here's 1, 2, 3. I'm trying to do these 4. Trying to do these evenly spaced, right? If the tick marks are spaced like this, what happens to them here? Well, this doesn't just rotate it. This actually rotates it and stretches it out. If you look at this, this doesn't have a length of 1. This vector, if you did its magnitude, it wouldn't be 1. So the unit vector for CT has to have a length of 1. Well, over here, it's longer than 1, which means these little tick marks, as we bend over, they actually stretch out further. Okay, and this is an indication of time dilation, right? The faster something goes, then the little marks on its axis, they actually stretch out. Time stretches out, it lengthens for this object. And I might go down here and redraw this graph just a little bigger and better than this. So let's take a look at that a little better. So let's say Here's my graph. That wasn't a good line, was it? But whatever, we'll go with it. Here's CT, and here's X. And as our axis bends over further, those little lines on it are little tick marks. Let me go back up to this one. These little tick marks, they extend and get longer. So if we go to an even faster moving object where its axis would bend over even more because V would be greater, so we'd have a bigger angle, well then the tick marks on it wouldn't be that far, they'd get spread out further and further. And this is an artifact of time dilation occurring. As this bends over, and of course as you bend over all the way to 45 degrees, then these would become, infinitely long. You wouldn't sense time anymore, but these spread out and get longer, okay? And so if we look at that rule carefully, it turns out that if we were to look at, say, 1 second going by, right? Let me draw in my my speed of light ray here, right? This is light going out 45 degrees. I think I could maybe do that line a little better than that, at least here in this part. So let's say this is our speed of light going out, okay, 45 degrees. What happens is if we have a spot on this axis where we are starting, say this is 1 second, right, along this axis, one second in CT time, ignore the C part, so it's 1 unit of time. Well then, the actual, as we bend over to different axes, how does this transform? And it actually transforms hyperbolic-like, which means it comes out this way and curves up, and it approaches the speed of light, but never quite gets there. So if we draw in any other axis, something that's close, then everywhere it crosses like this, everywhere it crosses that little hyperbola I drew in would be 1 tick. Let's say we had a clock, an identical clock on each of them. Well, this is where the clock would tick on the at rest, the quote at rest frame person. This is where it'd tick on someone going a little bit faster. It's not much longer. And then here it's a little bit longer, so time's getting dilated, then it's a little longer, and then over here you can see this line's significantly longer than this was, right? It would be, way up here. And so for this person, that tick on the clock took longer, and if you draw even another one getting closer and closer to the speed of light, as you go out here further, as that line goes out, you keep hitting this hyperbola further and further out. And so this would be a line where everybody would have 1 tick go by on their clock. And then 2 ticks, say, was up here, and then there'd be this other parabola that would go up like this, and it would approach, but never get to 0. And this would be tick number 2, and of course it stretches out for each of them. But it's hyperbolic. And the same thing for the x position. If this was, say, 1 meter, then 1 meter would curve over into this hyperbola, and as you went faster and faster, so there's not a lot of distance there, you're not a lot faster, but if you got out here and you went faster and even faster and went really near the speed of light, then that length, that 1 meter spot gets to be way out here and way out here. And so this can be a form of length contraction as this gets spread out along with that. And so this is a hyperbolic space. It's not a regular circular type space that you're used to, where you have that that kind of circular space going on, and what you're used to with the Pythagorean theorem and everything like that, where things kind of bend out in circles or these things stay straight. This is a hyperbolic space. You can't actually if you keep increasing your speed, you can basically travel along this hyperbola. You can't actually ever curve back around. Because if you could go back, if you could move down this axis, you would essentially be traveling backwards in time, and that wouldn't be allowed here, and this prevents it. Okay? Another thing we need to look at is this red line down the middle. If you notice, none of these lines can cross it. No one can cross over this line. They can't come down here and go past it, because this is the fastest thing in the universe. This is the speed of light. And in order for you to cross this line, one of these speed of light lines, you have to actually be going faster than light. So let's come back up here to this graph here, let's say. Or no, I guess I could just do one more down here. Let's take a look at another one of these. We're going to have to draw quite a few of these. So let's say here's CT, here's, so X, CT, here are our axes, and again, our speed of light line, speed of light line is right here, 45 degrees, get rid of that little mistake. And now, if you think about this, we talked before about uh, the space-time interval. And if you look at this, in order for you to cross this line, remember, if you look at this, the slope of this is going to be related to your speed, right? You have to travel slower than this. So what would be the speed of this guy? Well, it would be displacement over time, okay? And if this is equal to c, and that's our basically our maximum velocity. I shouldn't have written that there. One moment. This is our maximum velocity, the speed of light. Well, then nothing else can cross over this slope, right? So on our previous graphs before, where we had x on the vertical axis and time on the horizontal axis, the more vertical a line got, the faster it's going. But here we flip-flop the axes, so the more horizontal a line gets, the lower its slope gets, the faster it's going. So any object moving, say from here to some other places, it tries to move. Say we sent this thing off and we had it speed up. Well, at first it's going real slow. Well, it's going to speed and speed and speed. But the thing is, it'll never be able to speed up, right? The lower this slope gets, the faster it's going. It's the opposite of the way we did the graphs before. It can't ever actually get to a speed faster than this, right? So if I'm inside or above this light line here, if I'm above it, I can't ever get below it. I can't ever cross it, because the only way to cross it would be to have a speed like this. Well, this is a lower slope, and this is a velocity greater than the speed of light. And that's not something that, according to the special relativity and according to any of this isn't a possible thing to do. We can't go faster than the speed of light, and so we can't actually have that kind of motion. So any motion you do, you're trapped above this. And if you think about this and you imagine that, let's do one more of these diagrams here. Drawing a lot of them, they get kind of messy. But let's say instead of this light being emitted here, let's say it was emitted from here, right? Well, light would go out, let's say, in both directions. Like we emitted we had this flash bulb in our flashlight, and we flicked it and it flashed light and the light went out in all directions. Well, then what we would have is something called a light cone, because light would go out in the positive x direction at 45 degrees and it would go out in the negative x direction at 45 degrees. And so this could be even just something, the light from an event. This could be a star exploding. This could be someone opened a door. I mean, anything, any event that occurred, it occurs here. So we'll call this like event A. Well, if you're inside this light cone, if you're in here, if you were at event A, okay, you can't get out of this. Because if you think about this, time is always increasing. So this axis here, CT, you must always be moving up on. You can't ever move back down on it. That requires speeds greater than the speed of light, like this. You can't have that, and you can't go down this way, because that's going in negative time, and that's time travel. Or backwards time travel, which we can't do. So you can only move left and right, and you have to keep moving up at all times, because time keeps extending. If you were sitting still here at A, say you took a picture and the flash went out, if you were sitting still, then your positions would just map out a vertical line as you stayed right there. If you were here and you decided you were going to move to the right, then your positions at a constant velocity would map out a line like this. And if you were moving to the left, you would map out a line like this. And if you were moving all crazy, you might do something like this or something or other. You'd have some crazy line. But at no point could you have a slope, right? A slope that puts you faster than the speed of light. So a slope that was less than this 45 degrees, which means you can't get out of this. And this thing is called, this red boundary that you can't get out of, is called a light cone. And you cannot get outside of a light cone because you cannot go faster than light. And so basically this is telling you that you can't catch up to the light that you send out. No matter what you do, you can't get to some position, some space-time point before the light could. And if you think about that long enough, that should hopefully start to make sense to you. It's kind of one of those things you have to spend a little time going over in your head because these graphs are different than what you're used to. But you should be able to come up with it. It's like if I fired what this is telling you is if I fired a laser beam out, right? This is the laser beam. I could never catch back up to it. Okay, I wouldn't be able to catch up to that laser beam. This example I did right here would be catching up to the laser beam and passing it, because here you're going faster than the speed of light. But we can't do that, so no catching up to, no passing. You're stuck inside this light cone. It's called a cone because this is just the x-axis here, right? This is just the x-axis. If we had like a y-axis and a z-axis, then you could imagine that we'd have 45 degrees out, coming out along the y-axis and x-axis, and it would make like a three-dimensional cone that we couldn't get out of or do that. Now, what are these lines I drew right here? What are they called? Okay, so actually this light cone idea, that's a pretty big idea. But what are these lines I drew here, where I drew out all the positions that something took as they moved through space-time, not just through time, not through just space, but through space-time. These lines are called world lines. Okay? And they basically map out all of the positions in space-time that everything goes. Okay, so this event A is a position in space-time. It's not just a position in space or a position in time. It's an event that occurred at this location at this time. Okay, and then the same thing with right here. This person right here, they have a space-time coordinate. They're at this position in space, and they're at this position in time, okay? And this position back here, this person, whoever's world line this was, they can never go back to that spot. They could turn on their jets and travel back and be at the same position that they were previously, like they could go back to this spot in time, in space, but time would keep going forward and they'd be at a new space-time point up there. So this would be a space-time point. Once you're at it and you're past it, you can never go back to it. You can go back to the same position, but not the same position and time, because that would require you to travel back in time. Because remember, this has a time and position amount to it. Okay, so how do these events, how do these deal with our bending of axes, these space-time diagrams? How can we represent those and look? So let's say that how would we view events? So events in space-time. Well, if this is our unprimed axis, right? So here's x, here's ct, and then we have a primed axis, right? Same angle for both. Here's ct prime, and then I'll try to do that one, about the same angle, x prime, and then there was an event that occurred. Let's say it was a supernova or something, right? There's some event here, some exploding star or something, and it happened at this position and this time, okay? So it's a position in space-time. Well, how do we measure this space-time position in both our reference frames? Well, in the x and ct axis, it's really simple. You just drop a vertical line, okay? Go over horizontally, and this would be its position, and this would be the time at which it occurred in the unprimed axis, right? So you'd say, oh, that happened, so say you were sitting right here, you'd say, oh, that happened this distance away from me, and it happened after I sat here and waited however much time this was. So this could be an hour, and this could be 10 meters, and you'd say, oh, yeah, that happened 1 hour after I was sitting there, and it was 10 meters away from me. Okay, but what about the guy on the primed axis? What is he going to view this space-time position? And that gets a little bit trickier. Here, what you have to do, and it's actually the same thing you've been doing all along, you just didn't know it, and I'll use red, might as well. When I said drop this line vertical, you're not really dropping the line vertical. What you're trying to do is look at all the positions that are all the same. And what you're really doing is dropping a line that's parallel to this axis. And when you did this line, I said go over horizontally. What you're really doing is going along parallel to this axis. So if you can kind of keep that in mind, that you're actually moving parallel for the time of the position, you're moving parallel to the x-axis, and for the position, you're moving parallel to the time axis, down to the axis and making arrangement, then this becomes doing the same thing. If I want to know the apparent position in the prime axis, well then I follow a line that's parallel, right? That's this line parallel to my time axis. And this would be the position that the prime axis person would see it. So this would be x prime, like x1 prime. This could be sorry, I put a 2. This would be x1 unprime. This would be x1 prime. So this could be like when it first started to explode. So this is CT1. And then if I come along parallel to the x-axis, parallel to the x-axis, as close to parallel as I can get, then this is the space-time CT prime 1. And this would be the amount of time that went by between these two events. And so let's say that the event was when the person traveling in the CT prime axis passed by us. That's we're going to call that space-time point A. All right, that's our first event. The prime axis person passes by the unprimed person. So, unprimed person sitting here, floating in space, prime person, right, goes along and passes right by them. It's when they're lined up on the x-axis, when they pass right by each other. That's event A, okay? And then event B is this exploding star, right? It explodes. Well, if you look at this, look at how much time passed for the person sitting still. That's a greater, I'm sorry, I'm looking at the wrong axis. Look at how much time passed by for the person on the unprimed axis. That would be this person, right? They see a longer amount of time between when the other person passed them and when the star exploded, right? And then look at the amount of time for the person in the prime axis. It's a smaller amount of time. So their clock slowed down, whereas this person thought it was like an hour. This person only thought it was like 50 minutes because it's a shorter distance up that axis. And the same thing here. This is now, so that's basically time dilation that's occurring there. And then here, length contraction. If this is event A, look, this is how far he thinks it is away from the space-time point where they passed each other, right? It's a longer distance here. And this is how far away the prime person thinks he is from where he first passed a shorter distance, okay? So you can see that this bending of axis is actually giving us back time dilation and length contraction here in the same diagram, okay? And I mean, if you look at that, what I mean to say here is that we have, let me get a different color. We have this length here is shorter than this length here, right? That wasn't a very good line. This length here, right? So x1 minus a is bigger than x1 prime minus a, okay? And the same thing here. This length is smaller than this length, all right? So the same thing, CT1 minus position A, whatever that length is greater than CT1 prime minus A. So this is time dilation and this is length contraction, both visually represented in this this space-time diagram, this Minkowski diagram or Minkowski space, whichever name someone's going to refer to it as. But you see both of those things going on, okay? Now, the last thing I want to do is talk about how this actually goes along. Well, actually, I have two things. One, you can see this now. We could talk about the space-time interval, Remember that? Space-time interval. And in that, we said delta S, which is a space-time interval, is ct squared, c delta t squared, minus delta x squared, right? This was our space-time interval. And I said that if this was a positive number, right? So positive, where light traveled a further distance than they were separated. In other words, because remember, this is the distance light could travel between events, between time in a time t, and then this is the distance between the events. So if I have two events, say here and here, event A, or I shouldn't do A, huh? I should do event 1 and event 2. Well, then look at this. If I do this over here, this right here, this length here is c times t, right? And then this length here, this littler length, is delta x. Okay? So we'd have a delta x and a ct. Well, if you notice here, ct is bigger than delta x. And this slope is greater than the slope for, you guessed it, light. So if light had come from right there, I'm going to do it in a different color because I already have red on here. If light had come from this event, light would travel at a 45-degree angle, fastest it could be, right? Which means that something slower than light could have actually traveled between space-time position 1 and space-time position 2, or space-time event 1 and space-time event 2, which means they might actually be linked. So positive means they might be linked causally, like one could have caused two. If we have a negative space-time interval, right, between two events, then we'd have two events, like say, here's event 1, and then we could have event 2 or event 3, say between event 1 and event 3. Look at this now. For something to actually make it from event 1 to event 3, you would have to have, here is CT, right? It's this length here, and then, but delta x is this here. And delta x here, this would be the delta x this time. I know my picture's getting a little wonky, but delta x would be bigger than CT. And it would give you a negative space-time interval, which means that you couldn't have gone between them. Because if you look at this, in order to have traveled from space-time event 1 to space-time event 3, sorry, not 2, space-time event 3, you would have had to have traveled faster than light. If you were at space-time event 1, then the earliest you could even hope to get to where space-time event 3 occurred would have to be up here. You would only be able to get to that position sometime above this speed of light cone, this speed of light line. So if you were here at this point, the fastest you could hope to get there would be somewhere above here. That's the earliest you could get there, and this is outside your reach, so this is not, they're definitely not linked. And pay close attention to this. This might be linked, this is definitely not linked. So if you see a missile fired at 1, and then a planet or a spaceship blows up at 2, then you could think, you know what, it might have been the missile that blew up that space station. But if you see that missile fired at 1, and then you see something blow up at 3, there's no way that missile did it, because the missile couldn't have reached it in time, because not even light could have made it over there. Even if you were firing a laser beam, like a Death Star laser beam, the laser beam couldn't have made it all the way over to position 3 to blow it up. It would have blown up before it could have reached it. So this is how that space-time interval goes with this. And remember, this space-time interval thing here, this idea, it's a geometric idea, and it's almost like taking, it's almost like looking at a slope. It's more like looking at a Pythagorean theorem, just with the non-Euclidean, non-normal metric. We have a plus-minus metric here, so it does that. Okay, but this space-time interval, it's invariant, and everybody can agree on this, no matter what axis they are. If the people in the x-axis calculate delta s, the space-time interval, and the people in the x-axis prime calculate it, you'll get the same exact answer, and everybody can agree about whether or not events were linked or not linked. And remember, links that are definitely linked, or I'm sorry, definitely might be linked, these guys, there's no frame of reference that can reverse the order of the events, that could make event 2 seem like it happened before event 1, but there do exist frames of reference that can make event 3 appear as though it happened before event 1, because these are definitely not linked. So you can only reverse the order of events that are definitely not causally linked. Okay? And now the last thing I want to do is just real quickly touch on that twin paradox. So in the twin paradox, we said that it would be the one that the person that would be wrong in the twin paradox would be the one that changed their motion and went back. So if we look at the twin paradox here, and so this will make the Earth person right. Well, the twin travels off fast near the speed of light, and if you remember, every tick on the clock for the person on Earth is like this, right? But then this other person going faster, those get spread out, right? So here, you'd look at this and you'd say, oh, well, if this person then turned around and sped back over, the end of my line there is a little wonky. They turned around and they sped back over. One, I need to make this line longer. So let's say this continues on up, right? Tick, 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 tick. This isn't going to be perfect by any means, but if they were to turn around and speed back over here, tick, tick, like that, you'd count up these ticks, and this guy, you can see, has a lot more ticks if they had identical clocks, and this was a tick on each clock. Every hour the clock ticked or something, then you could see this guy had what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. He would say 17 hours. So this would be the guy on Earth. Earth says 17 hours, but the guy on the ship has 1, 2, 3, 4, 5, 6, 7, more like 8 hours. So 8 hours on the ship, right? Well, that's essentially the time dilation built in there. This guy turns around, comes back. He's now the one that's longer. But let's look at the reverse version of this, where the guy on the spaceship keeps going and the guy on Earth comes and catches up with him. So we'll do about the same angle, right? He just keeps going. Well, the guy on Earth waits with his slow clock, and this guy has his slowed down clock like this, right? However many there are. And the guy on Earth but then the guy on Earth, let's say he waits 1, 2, 3, 4, 5 hours, and then he decides that I'm going to go catch up to whoever this is, to my twin. And he rockets off really, really, really fast. And you notice this is a smaller slope. It's bent down closer to the speed of light, which means his time is dilated even more. And so I maybe made these spacings too far apart. Sorry, it's not going to be a great example. But you can see that during this time then, while he goes really fast, his time dilates even more. So he has a few hours waiting, and then he goes and catches up to him really quick. And I think I did these. I didn't space these out well enough. Sorry. I'm sure these tick marks should have been closer to those than I did. But anyway, the point is, you can see it would be during this time that the person on Earth's clock would slow down even more than the person who was in the spaceship's clock would. And by the time he would catch up to him, less time would have gone by. And here, Earth would have said something like, oh, it's only been 8 hours. But the guy on the spaceship would have said, oh, no. He would have said, no, 1, 2, 3, 4, 5, 6, 7, 8, 9. He would have said, oh, no, it's been 9 hours or something like that on the ship. Okay? And so that's basically, you can account for this time dilation, and we can answer the twin paradox using these. And if you did them out really nicely, you measured the angles correctly, you accounted for how much the time dilation would occur, then this would work out really well for you, and you would get what the actual answers would appear to be if we could assume to ignore these little times of acceleration. Because you have to admit, right here, he's changing velocity. Here it's constant velocity. He changes velocity. There's some acceleration here. When it comes down to it, it's actually during that acceleration right there that the time dilation occurs. And it would be during this huge acceleration here that his time dilation occurs. But that's general relativity stuff, and we're not really to that yet. But we can still account for what difference in clock speed see just by doing these space-time diagrams and just pretending the acceleration happened so fast we could ignore the amount of time that acceleration occurred in. Okay? I think that's pretty much everything.